First speaker for this 2018 season is Greg Landrum. He describes himself actually as a cheminformatics developer, climber, hiker and cook. He's formerly from Novartis and he's the pioneer of RDKit, which has been used by almost everyone for handling chemical structures and underlies a lot of software that you'll find on the web. He left Novartis a couple of years ago and he's now the VP of Life Sciences for Knime. And I'm sure that Knime is familiar to you. It's in fact a topic that Greg himself introduced in the short talk in this series earlier on, I think in about 2016. What he's going to talk about today are workflows and tutorials from the Teach, Discover, Teach competition, which he wrote with Serena Rinica. He's going to show you how to use them, how they were developed, and some of the results that they got from processing a malaria dataset. So over to you, Greg.
Thanks, and thanks for the chance to do this presentation. I am audible, right?
Yeah, I can hear you.
Okay, cool. So as Carolyn said, I'm going to walk through a tutorial showing a bit of how you can do processing high throughput screening results with Knime. I will start with a very brief introduction to Knime itself. I'm going to assume that people know it to some extent, but I'll provide you some resources, pointers to resources if you don't. And then I'm going to go through in some detail a workflow for doing processing of HTS results. We'll do a Q&A session at that point, and then if there's still time at the end, I'll show some other examples of doing chemistry in Knime with the RDKit, so some case studies and publicly available workflows for that. An important thing, this presentation as well as all the workflows and the data that I'm using here are available here. This is a Dropbox link on the other side of this Google shortener. That link will show up a few more times in the presentation, so if you don't manage to catch it now, don't worry, it'll come back up again. The workflows themselves are going to show up in the examples folder in Knime, and I'll show you what that looks like for those of you not familiar with it, but they'll show up later this week in Knime. I need to do a bit more cleanup before I can put them in the examples folder, and I just didn't have time to complete today. So let me tell you a little bit about Knime. It is an open source tool, the analytics platform, that is supported by a company. The company was founded in 2008. We have offices in Zurich, which is where I'm based, Konstanz in Germany, Berlin in Germany, and then Austin in the US. At this point, we're about 40 plus employees and we're growing fairly quickly. The main thing that we do is maintain the open source platform. So that's the majority of those people are working on open source code and the software that you perhaps have used already. Knime is released twice a year. So that means since 2006, which is when we first released it, there have been more than 20 open source releases, and everything on the open source side, everything with the analytics platform is free, freely downloadable, free to use. So everything I show you today is something that you can download and use yourself. There's no commercial software being used. Having said all that, we also have some commercial tools. And I'll say a brief word about that later, because it is important that the licensing revenue from selling that commercial software allows us to continue to support the open source piece. So Knime, for those of you who haven't seen it, is a visual programming environment for working with data. You have nodes that you connect together. The lines between them indicate data flowing. Knime has multiple visualization tools available, as well as a bunch of different tools for bringing data in from multiple different places. This is just a quick example. When you download Knime and install all of the open source extensions, you end up with around 2,000 nodes that you can work from. And this is a very small subset shown here. We have a bunch of nodes for collecting to various data sources, reading from almost any file type you can imagine, as well as connecting to databases. That includes connections to big data resources, to Hadoop clusters, for those of you who know what that means. Once you've read the data in, you typically need to transform it in order to work with it. And we have a large collection of nodes for that. And then doing data mining and data analysis, which is the thing we talk about the most because it's kind of the most interesting piece of this whole process. Once you've done the analysis and data mining, you can then do visualization. We have a large collection of nodes for that. We also have connections for here, as well as on the transformation analysis part. We have connections to other open source tools. So we realize that as much as we can do inside of Knime, there are always going to be other tools available that do interesting things. And so we try to enable the use of those tools as much as we can. So for example, we have very strong integration with R, which is a standard statistics package. We have very strong integration with Python. And these are two of the big tools that are used by other people. So now you can read data inside of Knime, you can work with it with your Python scripts, and you can still have it then available afterwards in Knime again. Once you've done all your processing you want, we have a bunch of different ways for doing reporting the results out. So you can go to PDF, you can go to Excel, you can go to most any file format you can think of. And I'll show examples of that later on. It is somewhat overwhelming. You have this big package with all of these nodes. So we're trying to figure out ways to make it easier for people to get started. One of the ways we're doing that is we have the free e-learning course now, and it's available from knime.org. There's this introductory course. This is a series of small units that don't take very long to complete, that include exercises and solutions that allow you to learn how to use Knime in kind of a structured way. We're continuing to expand this. We're thinking about ways to take this initial e-learning course that's currently available that focuses on just general data analysis tasks. We're looking at ways to do a chemistry-specific version of that, because we do have a lot of chemistry users. The open source platform is the thing that you use. So if you're using Knime on your desktop, that's open source. We also have a commercial tool, which is the Knime server. The server allows you to share workflows with other people. So within a company or within an organization, you can share workflows and you can share data through the server. It also does things like access management, so you can protect data from people who are not supposed to see it. It allows you to do remote execution and scheduled execution. So if you have a job you want to run every night, you can do that easily with the server. And finally, it lets you deploy the workflows that you build. It allows you to deploy them as a web service or a web application, which is also a useful way to communicate and collaborate with colleagues. Okay, that was my introduction to Knime. Let's move on to talk about processing HTS data. Oops, sorry, wrong way. The background for this is we're going to be processing a hit list from an HTS screen for malaria. The two steps that we're going to do today is take the hit list, we're going to clean it up, which I'll explain as we get to it. And then once we've cleaned it up and have hit things that are probably real hits, we're going to suggest compounds that are going to be sent to the validation assay. Right, so these are the first two steps of that kind of standard workflow for processing data. You get the raw HTS data that comes in, and then you need to pick the compounds that are going to be sent out for validation for that IC50 or higher resolution measurement that you'll then use to make decisions for later processing. The data source here is from the 2014 Teach, Discover, Treat Challenge. For people who don't know what this was a nice program that was organized by the Comp Division inside of American Chemical Society to encourage people to put together workflows, tutorials for solving typical problems in computational chemistry or cheminformatics. The 2014 was the last time this was done. The group that organized this put together a couple of different challenges. This HTS is just one of them. So they put together a couple of different challenges. They had a bunch of new data that was generated for this challenge. Some of that data was published for people to work with, and some of it was held aside to verify or validate how well people did on the challenge. So it's an interesting way of working. The restriction for this is that whatever you did as part of the tutorial had to be done using open source or at least freely available tools. So the idea is these tutorials would come in and they would be available for anybody else in the community to use later, and they would actually be able to use it. The tutorial, the workflows that I'm showing are the first two steps of the tutorial that Sarina Renneker, who was a postdoc in my group at the time of the tutorial that she developed. That tutorial, which is linked down here at the bottom, goes on to do a number of other steps, including building predictive modeling and suggesting the next round of compounds that should be purchased. So there's a machine learning piece of this as well. What ended up happening with this particular challenge, there was a winner of the best overall model accuracy, and then there was an overall TDT winner. Serina's workflow happened to be the best overall winner. And we got together with the group that did the best, that won the modeling competition, the modeling part, and published an open access article that came out last year, the second version of that. So the response to the editorial, or the editor's comments, sorry, reviewers' comments, just appeared a couple days ago. So that's the link down here at the bottom. This includes a complete description of what we did, as well as links to the various tutorial resources, the data, and explanations of what the experiments were. Okay, so remember what we're doing here is we're going to clean up the hit list. That's the first step, and then we're going to figure out the compounds that we want to send on for validation. The approach we're going to take for cleanup is we're going to start by removing ugly molecules. These are things that include compounds that have panes. For people who don't know panes, these are substructures that have been identified that are likely to interfere with assays. So since a lot of high throughput assays involve fluorescence, there's a lot of things, a lot of the panes filters involve identifying fluorophores, or they include reactive groups and things like that. The other filter we're going to use is the REOS filters. This stands for Rapid Elimination of Swill. These are things developed by the group, Pat Walters and the group at Vertex in the early noughties. The references down at the bottom. This is basically looking for molecules that are too big, too complicated, or too greasy. Both of these sets of filters, REOS and panes, are rules of thumb. They're obviously not hard and fast. So just because you violate REOS, those rules think your molecule is swill, or because a molecule has one or more panes alerts, it doesn't automatically mean it's bad. So it's really important to look at the things that get filtered out of this and have a chance to rescue them. So the workflow that I show you, we will look at the outputs from each of these filters and manually have the ability to manually pull compounds back in, even though they look like they're bad. Once we've picked the compounds once we've filtered out the compounds that are likely to be bad or to be interfering with the assay or just too ugly, we need to pick the compounds that we'll send on for the validation assay. The constraint here is we would like to have good coverage of the chemical space. So this particular assay, there were about 1,500 hits. We want to have good coverage of the chemical space of those 1,500 hits, but when we generate validation results, it'd be really nice if we also had a bit of structure-activity relationship that we could learn from that. So the way that we chose to do this, the approach that Serina proposed in her tutorial, is to start with a diverse subset of the actives. So if we want to suggest 100 compounds, for example, we would start with 20 diverse compounds and then pick 4 compounds around each of those, 4 neighbors of each of them, so that we have a bit of SAR in the results. Let me show you what that actually looks like. This is an example. I'm jumping way ahead, but this is an example of some of the cluster centroids that we picked. So each of these molecules that are shown here was a hit in this assay in the phenotypic screen. And we would like to have these compounds go through, but we would also like to have a little bit of something around them so that we can learn a little bit about the SAR. So the next slide here, we show for a particular compound, this was the cluster centroid, and these are 3 neighbors around it. So you can see when we screen these 4, we will at least pick up a little bit of SAR information, more than if we just did this compound by itself or a number of diverse compounds. And I show here 2 examples of the cluster centroid and the neighbors around it. So that's the idea. We're doing 2 things. We want to have good coverage, so we do a diverse pick initially, and we want to have a bit of SAR available, so we pick neighbors of each of those compounds. This is what the workflow looks like for the cleanup. It's fairly complicated, so I broke it into 2 parts so you wouldn't be able to see anything. We're going to walk through this. I'm going to do a slide demo. I'm not actually going to open up Knime and do that. I'm not brave enough, I'm afraid, to really try and do a live demo via WebEx. But so we'll go through each of the nodes. The top piece, we're going to read the data in. So we're reading in the data from the the raw data that we were sent from the experimentalists. We're going to filter out the columns that we're not interested in, that were in that data, and also indicate which column is the active column. Then do a bit of cheminformatics, do the REOS filters, do the panes filters. So let's look at each of those in turn. This gray node is a wrapped meta node in Knime. There's a bit of additional functionality hidden inside it, but it gets a dialog automatically. So if I double click this, I get this configuration dialog up that pops up that allows me to pick the activity column. So this is one of the columns in the data set that has whether or not the compound is flagged as being active. And then it allows me to remove columns that I'm not interested in for the later analysis. In this particular case, because each of these compounds has already been tagged by the experimentalist as to whether or not it's a hit, I'm not interested in having the raw fluorescence results. Which is what these two columns are. So I just take those readouts out and move forward with just a sample ID, whether or not the compound's a hit, and then the smiles for the compound. The next step is to go and calculate the properties that are required for these REOS filters, this rapid elimination of swill. So these are just a few cheminformatics parameters. So it's the size of the molecule, or an approximation of the size, some measure of complexity, and how greasy the molecule is. So I calculate that here, and then what I want to do is show the user the compounds that were filtered out. So this row splitter basically takes each of the compounds, and the ones up top do not have any REOS flags, so those are good molecules. The ones down at the bottom have been flagged as violating one of the rules. So this next node down here is going to show me those molecules and allow me to pick any of the ones that I might want to rescue. I'll then take those I'll take those molecules, add a column to the table that says, okay, I rescued these manually and I rescued them because they were, or even though they were REOS violators. And I concatenate those two tables together and then take everything forward. So this node, when I execute it and look at it, basically it just pops up a table. In that table, you have the pictures of the molecule, you have all of the data that came in, and then there's also this additional column that has the REOS rule that was violated by the compound. So I can sort on this and browse through and look at the ones that I'm interested in keeping, even though the rules say that it's, this compound's likely to be no good. So after I've done that, I move on. I then take all of the remaining compounds and look through them to see whether or not they have any of these panes substructures, these substructures that are likely to have interfered with the assay. The same thing happens here. Any compound that does not have pane filters goes out the top piece. Sorry, anything that does not have a panes match goes out the top branch. Anything that does have a panes match goes out the bottom branch. And here again, I'm going to show the compounds to the user, allow them to take a look at them, and take any compound that they're still interested in keeping, flag it, and have it come back in and get combined with the other ones. So here is what the view of that node looks like. This is a little bit different because it shows the compounds and it also highlights the panes match in the molecule and shows what it is. So for example, this compound, the highlighted substructure is this particular panes filter, so it's an aniline. That's been flagged up. This has actually I don't remember what H zone stands for, but it has a phenol that the system is unhappy with. And in each of these, you can see the flagged substructure and you can decide whether or not you're interested in taking a molecule forward. For demo purposes here, I just flagged these two molecules to bring forward so that we can see them later. But again, it's the same thing as with REOS. We want to take these rules of thumb and make sure that we have a chance to identify the cases where they flag something that we're interested in seeing, even though they violate the rule of thumb. Okay, this is the second part of the workflow. So I have the things coming out of the previous part. I have the compounds that have been rescued, or the compounds that had no bad flags, and also the compounds that the users rescued. I combine all of that data together. I'm not going to get into the details of this. I combine all the data together, and at the end, I'm going to write out an Excel file. This is what the final data looks like. This is the output of this last this last node. This is a standard Knime table. You can see here the structures. There's this rescued column. So any compound that I rescued manually, I've captured why it was rescued or from which filter it was rescued in the output table. So that later when this compound comes up, we can say, oh yeah, that has a Payne's filter, but we believe that it's okay. Or in this particular case, this compound was filtered out by Rios. We believe that it's still okay. So we brought it forward manually. And then finally, the last piece of this, perhaps the most important piece, is we're going to write the data out so that we can look at it and pass it on to our colleagues. In this particular case, what I'm doing is writing out an Excel file. That's not, of course, the best thing to do, but people like Excel, so we're writing Excel out. And this is an example of what that spreadsheet looks like. So you can see we have pictures of the molecules and then all of the data that came out from the all of the data that came out of the Knime table, again, including this column about whether or not the compound was rescued. So that's the first piece of the workflow. We've now flagged the compounds that we believe they don't have any problems in the, or they don't have any of the flags that would indicate that they're likely to have problems in the high throughput screen. Now what we're interested in doing is taking those hits, those cleaned up hits, and pick the compounds that we're going to move forward for the validation assay. And as I said, for that, we're going to do this two-step process of picking a series of diverse seeds and then picking neighbors of those so that we have a bit of coverage of the chemical space and then a bit of SAR. And then in the last step of this, we're going to have a manual filter where we can actually look through the compounds and throw out the ones that we don't like. So let's go through this again step by step. The first node here that allows us to pick diverse seeds, if we double click on that, we get a dialog that allows us to say the number of clusters we want. So this is the number of diverse seeds. In this particular case, we'll take 20. Click OK, it does the diversity pick and then shows us each of the cluster centroids. So this is the filter seeds node. When we look at the view in that, we can see for each of those, we see the centroid and the experimental data on the centroid. Here, if there are structures in here that we don't like, that we don't want to see neighbors of, we can exclude them by just clicking anything, clicking rows in this table. So anything we click here will be excluded from further analysis. So we won't pass that on. We won't find neighbors of it. We won't suggest that for further screening. Moving on, we now want to take those seeds that we picked, those cluster centroids, and identify neighbors to get to a total number of compounds we're interested in. So in this particular case, we want to get up to 100. So now we're going to have that do a, well, I'll show you what we're going to do. Sorry, I don't have that slide. Apologies. So what we're going to do is, again, for each of the cluster centroids, we're going to look at around it in chemical space, find the things that are similar to it, and add them to the output table. We have 20 cluster seeds that we picked here. We want a total of 100 compounds. So basically, we're going to pick 4 neighbors for each of those cluster seeds. At the end, as I said, we then showed a view to the user that shows all of the compounds that have been picked, so all 100 compounds that have been picked, and allows them to look through them, find anything that they don't like, flag that for exclusion, and then at the very end, everything that has not been excluded by the user is again written out to Excel. And this is now our final result we have for each compound. In this table, we have the experimental results that were generated so far. We have a picture of the structure. For the compounds, in this particular case, with this diversity picking scheme that we're doing, we have an additional column that says which cluster it is. So for example, we have, this is the experimental sample, or the sample ID of what was measured. This is the centroid sample ID. So this is the cluster centroid. This is one of the neighbors. So for each of these compounds, as we pass them on to validation, when results come back, we'll be able to map results to clusters and see what kind of SAR is present. Again, the workflows that I just showed you, those are all available with data at the link shown here. The PDF for this presentation is in the same directory, and we're going to put the workflows on the example server in Knime at some point this week. For those of you who don't know, if you're in Knime, in the Knime Explorer, there's this examples tree entry available. You right click on this and click login, and the login happens automatically. And the examples are going to be, the examples I just showed you are going to be in this 50 applications folder. So there's going to be somewhere down at the bottom, there's going to be 32 or 33 hit list analysis, and that's where all these workflows will be. At the moment, they're still just in Dropbox, so I need to clean them up. Okay, before moving on and doing a brief introduction of the RDKit and looking at some chemistry use cases there, are there questions on what I've shown so far? We have time for that.
Okay, if anybody has a question, you can either type in the question box and I'll ask it, or I can unmute you if I can find you. So, actually, Greg, one brief thing. When you wrote out your Excel file, you had the structures in the Excel spreadsheet. So did you have to use the reporting system to do that, or how did you do that?
So inside of Knime, and this is just using standard Knime functionality and an RDKit functionality. So there's a node here which is render to image. This is just taking the smiles column that's in the data table and just converting that into an image. And then Excel just has the image in it.
Okay, that's great.
So what you see,
about smiles.
so those are in there too. It's important to have that because then you actually have the chemical structures. So let me find the Excel. So this is the Excel. There is the picture so you can see it, but then there's also this column that has the smiles. Right. So there's something for the chemist and then there's something for the people who want to use it later.
Yeah, that's great. Thanks. Right, so we've got some questions coming in now. So we've got one that says, what about picking inactives for the training? That's from Daria Goldman.
In this particular case is just looking at picking compounds for the validation assay. The deciding what to use for the training set for machine learning is a separate workflow, a separate part of the overall workflow that's in that tutorial, in Serina's tutorial. One thing I forgot to say, Serina's tutorial is Python based. So if you go to GitHub, you'll see there's a really nice notebook she did that has a lot of text explanation, but it's Python in the end. What I'm in the process of doing is taking the pieces of that and translating each of them into Knime, and I've not gotten to the point yet of picking of doing the machine learning pieces, but that's coming.
Great. We've got another question here from Mark Gardner. It says, "Hi Greg, nice workflow. How often did you find 4 reasonable analogues to pick for each hit/centroid?"
That's a very good question. I didn't have to look too hard to find centroids that had reasonable neighbors, and I think that that's a property of this particular data set. So there were 1,500 hits, which is a good number. I mean, you don't often get that many hits. There were 1,500 hits, and there was enough. There are enough chemical series in the deck that was screened that this actually worked. But it's a great question. It is certainly not always the case that would be true.
Great. I should also say, Greg, if you give me the links, if you send me the links when you're all done, we can post them on the MMV website as additional information for anybody.
Okay, cool.
In this. Okay, we have any more questions? No, you've got thanks from both the people who asked the questions. So do you want to go on and talk about some RDKit for a bit?
Sure. So let me do a brief intro to that, and then I'll walk through some workflows in the same way I did the ones that I've shown so far. The RDKit is an open source cheminformatics toolkit. There's a lot of words on this slide. I'm not going to read them all. Don't worry. The big thing, the most important take-homes from this slide are the URL. So of course, if you Google for RDKit, you'll land on the same page, but it's nice to have the URL there. The software packages, I'll flag up a couple of things that are important. One is that the way that the software, it is open source software, but it is licensed in such a way that is very business friendly. So it's very easy to integrate the RDKit into commercial software. And that's something that I, as the primary developer and the other developers on a project, consider a very good thing. So we're happy to have people using it in the community. We're happy to have people using it in industry, and we're also happy to have people using it in software companies. We do releases every 6 months, just like Knime does, staggered a little bit, not the same time. So we do a release in March and then a release in September or October. There's a pretty big and active community, which is a great thing for us. It means anytime when people ask questions on a mailing list, we end up with a lot of questions or a lot of answers, a lot of people to answer them. It has a lot of the standard chemical functionality that you would expect in a 2D toolkit. It can do a number of different fingerprint types, which is important for machine learning applications and also chemical similarity applications. It calculates a bunch of descriptors that you would use, you can imagine feeding into machine learning models. And it has some 3D functionality as well. So it has a very good conformational analysis tool or software for doing conformational analysis, doing 2D to 3D conversion. This is also what's been published in the last couple of years, the way that we do this. That's also from Sarina Renneker, actually the same person who did that TDT workflow. And then we have some force field implementations to clean structures up. We also have a very strong focus on integrating with other pieces of software. So the RDKit, the core pieces are written in C++. The reason that that's important is it allows us to use the same code from inside of Python. So the notebook is what Sarina used to build the two original versions of the tutorial. I was actually doing the tutorial, redoing it in Knime. I was using this code in the back, so it's really important. That's important because when I generate the descriptors here, when I generate the log P and the fingerprints and things like that, or if I generate them here, I get the same result, which is nice. I don't need to worry about that as I'm moving the tutorial from Python to Knime. The RDKit has very good Knime implementation. So this was the original version of this, and it's continuing to be done. The original version was done by my group at Novartis. They're continuing to maintain that. We also have a lot of support coming in from the open source community there, making suggestions about node status, bug reports, etc. The kind of things that you can do, I show a list of nodes on the right-hand side. I'm not going to go through them in detail, but the kind of things that you can do are the types of things I talked about previously with the RDKit. So you can generate descriptors, you can generate fingerprints to feed into machine learning, you can do structure cleanup, so the kind of things that I was just showing earlier in the cleanup workflow. There's a bunch of stuff for doing substructure searching and filtering, and there's some really good reaction support. So I'll show an example of that as we move on. And then the last piece, of course, is the 3D stuff that I talked about, the generation of 3D structures from a 2D molecule. So you give it a drawing and you get back a 3D structure. That nice conformation generator is also available from inside of Knime. I'm going to show a couple of different demos. The first of these is a problem that happens fairly frequently. You have a set of compounds, so something for example, it came from a paper or from a patent, and you would like to find a scaffold for that. The way that we approach that here is we read the compounds in, we do a fuzzy maximum common substructure. So this is looking for the biggest piece of molecule that covers at least 80% of the molecules. And we then do an R group decomposition. We highlight that on all the molecules and do an R group decomposition. So let me show you what the results of this looks like, and then I'll say a little bit more about how this happens. This is the R group decomposition that comes out. The molecules that I'm showing here are from a paper that was pulled from Chembl, so from the big open source or open data collection inside of Kemble. This is from a single MedChem paper. And apologies, I don't have the reference up here. But what you can see is I have the maximum common substructure. This is the scaffold for the molecules in that paper. And then what the workflow does is an R group decomposition. So you get the scaffold for the paper, but you also get all of the R groups, and you can see what chemical space was explored by the authors of the paper. The scaffold, this is not, identifying scaffolds from a set of compounds is not a well-defined problem. There's no one right answer to this. I said the way that this is doing it is this kind of fuzzy MCS, so it's a maximum common substructure that has to cover at least 80% of the molecules, and it ignores atom types. So you get things, if you have a ring in your core that can be a phenyl ring or a pyridine, you can end up with an MCS that represents both of those. The workflow that I showed is on the example server. So I showed you that example server already. This is in the community section and in the RDKit section under that. So this is find scaffolds and side chains. Demo number 2 is a typical chemistry problem. This is library enumeration. This is also taken from the public example server. In this particular case, what I want to do is enumerate a set of compounds coming out of a where I'm forming amide bonds. The workflow goes here. At the beginning, I start by reading in a catalog. This is a collection of fragments pulled from the zinc database, and that's a set of commercially available compounds. At the end, have a reaction. This is the amide bond formation. So this is expecting amines to come in on the top port and acids, to carboxylic acids, to come in down on the bottom port. So what I need to do is take the catalog that I have and filter it down so that I have amines coming at the top and carboxylic acids at the bottom. And I'd also like to remove things to clean stuff up a little bit. So I start using this RDKit functional group filter. For the top branch, I say I would like to have, let me show you what that looks like actually. For the top branch, I want to have a single primary mean. So I clicked primary mean and set the qualifier equals 1. And then I also want to have no secondary amines. So there's exactly one amine in this molecule. It's a primary amine, and that is then what's going to react in the amide bond formation. I do something similar on the bottom branch. I just say I want a single carboxylic acid. You can also use this node to remove other things that are going to interfere with the reaction. So this is just a very simple example. But when I do this, I pick all of the amines that come out from this subset from zinc. I pick all of the carboxylic acids. Because there are too many of those, I then just subset down to take 100 of each of those and then feed those into the 2-component reaction node. What comes out the other side is a table that has the final products. So these have the results of forming the amide bonds. And then you also have the 2 reactants leading into it, so you can see where that came from. So again, this is just a very simple example showing how you can, in a relatively straightforward way, go from a chemical catalog and then do reaction enumeration just to explore chemical space to see what kind of space is available based on the building blocks that you have. Sorry, what kind of space is accessible to you based on the building blocks that are available. This next workflow is also from the public server. This is a somewhat more involved one. This is looking at another very common use case, which is identifying the compound in a patent. Again, there is not a single right way to do this. This is just an approach to doing it. What we're going to do is read in the set of structures from the patent. In this particular case, we're going to bring in the structures from the patent for Tarceva. I got that patent, or I got this structure by finding the patent in Kemble, exporting the structures. This is a very easy thing to do. I just exported them as a text file. So I read that into Knime. I'm going to remove the duplicates from that and add some descriptors and fingerprints. And then we're going to go in and start looking at the data. Because these computer-generated exports, the computer-generated structures that are pulled from patents are somewhat dirty. They include all kinds of bizarre structures, fragments, and other weird things. It is important to do a cleanup step. And so this That's what this node does. If we execute this and take a look, what you get is this visualization that shows I have a series of range sliders at the top that allow me to limit the molecules that are going to be passed out by the number of heavy atoms, by the number of rings, and the number of rotatable bonds. I also have a parallel coordinates plot here that shows me all of the compounds, and it then shows me the molecular weight of those compounds, the number of rotatable bonds, number of heavy atoms, and number of rings. The interesting thing about this plot is I can do selections around the individual axes and then see what those structures are in the table on the right. And so you can see what I did here is I selected the two compounds that have the highest molecular weight, and I'm just showing those over in the structure table on the right, and you can see what those are because I was a little bit curious. These are quite a bit higher than everything else, and you can see what that's coming from. This is obviously a catalyst. It's a bit difficult to see, but there's a palladium in the middle of that. So this was a catalyst that was used in the synthesis in that patent. Once I'm happy that I filtered out the garbage here, or at least filtered out most of the garbage, I'm then going to move on to the next node. And here I'm going to build a network. And I build the network by generating fingerprints for all the molecules and connecting things that are similar to each other. So molecules that have a lot in common with each other. I'm going to build the network, and then the next node I'm going to show that network. So this is here. I have filtered out all of the singletons. That's what the slider up at the top does. I filtered out all the singletons and really small subnetworks, and this is the main core set of molecules that are present in that patent. Each of these nodes represents a molecule. Again, I have a table. All of these things are connected to each other. So if I select compounds in the compound network, I can see them selected in the table. If I select things in the table, I can see them selected in the compound network. The interesting thing here, what we would like to see is, can we highlight, or can we find some way to flag the compound that is the key structure in the patent? In this case, is it Tarsiva? And it's not an accident that I pick an example where everything works perfectly. This first compound, when sorted by this hub score, which is a measure of the importance of the molecule to the overall network, the first compound here is Tarsiva. If you do this for a variety of different patents, this does not always work that it's the first compound, but it tends to be fairly highly scored. So this is a reasonably robust way of finding the key compound in a patent, or at least things that are related to the key compound. As I said, there's a lot of different ways to do this. This is just a nice interactive one that allows you to explore the space a little bit and decide what you want to do. That is the last of the examples that I have. So I showed you finding the scaffold for a set of compounds. I showed you doing chemical reaction enumeration, and I showed you identifying a key compound from a patent. All of these were taken from our public example server, so these are all some you can get to. Example server has a variety of different other examples in it, and we're continuously adding more as we develop them. So as I said, everything from this particular presentation will eventually end up in example server once I've had a chance to clean it up. So again, everything I just showed you is available at the link. This is how to contact me if you have any questions, if you'd like to follow up. I'd like to thank you for the attention and answer whatever questions people may have, if there are any. Thanks.
I'd like to thank you very much. Thanks, Greg, for a great presentation. If there are any questions, please just type them in the box. I've got a couple, so I get to ask those first. So there are a huge number of community nodes available from Knime. Which do you find the most useful, obviously, apart from RDKit?
So I almost tend to install all of the trusted community nodes. So the Knime in Knime itself, if you download Knime, you can go and there's a box you can to install new nodes, and you identify the trusted community ones. I tend to install all of those because I find myself using them not constantly, but reasonably frequently. The ones that I use the most, or that I've been using the most recently, there are a number of nodes in the Vernalis extensions that are just fantastic. And there's a number in the Earlwood extensions that I also find really super useful. That has a really nice 2D, 3D scatter plot that's super cool for exploring data, as a couple of other things. Those are the two that I use the most.
I think I'd agree with you on those. Now, in your patent example, you took the structures from Shaw Kemble. One thing that we've been trying to look at is there a good way of tying up the structure with the activity from the patent? So is there a good way of mining the activities?
There are examples out there of doing that. I've not explored those. So sometime last year, or I think it was last year, it might have been towards the end of 2016, but I think it was in 2017. There was a publication / blog post from Matt Swain, and other people have looked at this at figuring out ways to extract data from patents and link it to the compounds. I have not played with that, so aside from mentioning that publication and the software for that, I can't provide more concrete information than that.
Thanks. I think I know the publication you're talking about. So, any questions from anybody else? Can't see anything typed in the box.
No, I forgot. This was the other slide I was supposed to show. If you're interested in either of these topics and you happen to be free in 2 weeks, we have our Spring Summit, which is basically, it's like a user group meeting, but it's not just for users. This is a big event, between 200 and 300 people. Actually, we're hoping to break 300 this year. Monday and Tuesday are training. If you're interested in that, and then Wednesday and Thursday are summit sessions. We'll talk about things that are new in Knime and things that are coming, as well as have a bunch of presentations from our users and customers. And then on Friday, workshops. And there's some interesting things going on there, including some fairly nice life science focused workshops that are coming. That was supposed to be the last slide I closed with.
Sounds like it's going to be a great event. I hope you all have a great time. Okay, if there are no more questions, I'll just close the meeting by saying a huge thank you to Greg for putting all that together. We hope to. I will put the recording up on the MMV website, and you'll be able to access that. And hopefully, we'll be able to also put the link in so that you can download the workflows and perhaps Greg's slides as well. Okay, thank you very much, Greg.
Thanks for the chance to talk, and thanks to everybody for the attention.
Great.